This video discusses symmetry. We are going to be looking at 3 different kinds of symmetry. We're going to look at line symmetry, rotational symmetry, and point symmetry. Starting with line symmetry, many natural objects have symmetry. So here's an example of German Shepherd maybe. And for people also, you can actually make this line of symmetry, vertical line, that basically splits a face in half. And we can see that one side looks very much like the other side. They're mirror images of each other. Something has line symmetry if you can fold along a line, and then each point, when folded, would line up with another point on the other side of that line. Now, not everything has symmetry. Some figures like this one have one line of symmetry, and you can have more than one line of symmetry. So, for example, looking at some other places in nature where we can see symmetry. So butterflies are a really good example. Our line of symmetry is right here, and the rest of it is a mirror image of each other. If you saw the video that I did on the reflection transformation, very much the same idea. Over here, we've got some creepy crawly. So I see a line of symmetry going this way. If you folded it in half, you could make an argument that there is some kind of symmetry going this way, perhaps. Maybe it's not exact, but I do see some kind of symmetry going in another direction as well. The alphabet, and I'm looking at uppercase letters of the English alphabet. A lot of the letters will show symmetry, and we're going to look at symmetry in letters and words a little bit more in a moment. And our polygons can also show symmetry. We'll discuss that a little bit further as well. Let's look at line symmetry with uppercase letters. I've drawn them across the top here, and I'm trying to determine how many of these letters in this top row over here have vertical line symmetry. Vertical means straight up and down. I'm looking at this uppercase A, and I can actually fit this line of symmetry here, where in your mind you have to imagine you're folding along that line. All these points on this side will match up with all the points on that side. A does have vertical line symmetry. The letter B, however, there is no vertical line I can draw there that will show symmetry. Uppercase B, as written here, it does not show vertical line symmetry. Same thing with C and D, right? C, D, E, F, G. I'm looking at all of those, and in my mind, I'm kind of putting through these vertical lines. I don't see the symmetry where it's making a mirror image. However, when I get to H, if I can get that sort of in the middle, hopefully you can see that H does have vertical line symmetry, and I, it does as well. But J does not, K does not, L does not, M does, N does not, O does, P doesn't, Q doesn't, R doesn't, S doesn't, T does. U, as drawn here, does. If you were to put the little tail on it, some people draw U like that, that would not show symmetry, but the way it's drawn here, it does. And then V does. So let's see, I'm falling behind here. U does, V does. W, yep. X, yes. Y. And Z, that doesn't. It looks like, how many do we have? Looks like 11 of these uppercase letters will show vertical symmetry. Let's look now at horizontal line symmetry. So let me erase what we've done, because now we want to look in a different direction. Horizontal, that's like the horizon, so going this way. So A, I can't find a line that's going to cut it in half to make two mirror image sides, so no. Now B, I'm going to say yes. I've had some picky students say no because it's slightly smaller here, right? If you draw your B's like that, it doesn't. For our intents and purposes, we are going to say B, it's the same. So yes, we're going to say B does. C, that one also does. D, and basically what I'm thinking about is if I were to fold along that line, or is there a line that I can create that when I fold, we get mirror images that will line up? E does. F does not. G does not. H does. I does. J does not. Now K, I'm going to say K does. K is another example where, kind of like B, depending how you draw it, for our intents and purposes, K does have horizontal line symmetry. L does not, M does not, N does not. And I have a lot of people who get confused with N. They think maybe it does. Now, that's because our brains are very wired to recognize symmetry. N has a different kind of symmetry, but it's not horizontal line symmetry. And we'll talk a little bit more about what kind of symmetry N has, along with some other of the letters, in a little bit. But let's see. Horizontal symmetry, yes, O does. P does not. Q does not. R does not. S doesn't. S is another tricky one that some people think, well, maybe it does, but it does not. T, U, V, W. Oh, X does. Y does not. And Z, again, it's a third letter that I think some people have trouble with. But I think these are all the letters that are going to show horizontal line symmetry for our uppercase alphabet. 9 of the letters, uppercase letters in the alphabet. Now, the third question says, how many of these letters are going to show both horizontal and vertical line symmetry? And they mean at the same time. They're basically saying from this set of letters we found in A and this set of letters that we found in B, what's the intersection of those sets? That is, what letters are in both places. So looking and comparing the letters, it looks like H is in both of them, I is in both of them, O is in both of them, and X. These are 4 letters that are going to have both vertical line symmetry and horizontal line symmetry. The last question here, words can also show horizontal or vertical line symmetry. So I have a few examples here. So mom, that is a word that has a vertical line symmetry. If I kind of fold it along the middle there, everything will line up, and wow does as well because, well, these words do look kind of related. You can have horizontal line symmetry as well. So a word like cook. So if you were to fold along that line, those letters would all show that same symmetry. So the question is, okay, what's the longest word you can think of? So you can play around with it and think of some different words. I have a few ideas. Cookbook. Right, that would work. And there are others. Checkbook, maybe that's a little bit longer. But if you want to have just a fun little exercise of thinking of words that can either fold along horizontally or vertically, go ahead and do that. We're going to look at a few examples with line symmetry. We've got some shapes here, some in nature, some are just polygons, but how many lines of symmetry do they have? So let's draw those lines of symmetry. When you're looking at something like this sea star, it's a 5-pointed, very symmetric looking star. I could actually draw a line of symmetry right here. And if you can think about it, if I were to fold that sea star along that line, these points would line up. All the points would have a matching point on the other side. That's one, but I can do that at every point. 1, 2, 3, 4. That would be 5 lines of symmetry. This one actually has 5 lines of symmetry. This kind of a little flower petal here. I can see one going this way and I can see one going that way. So there's at least 2, but I can also go this way and that way. So I've got up to 4 lines of symmetry. But if you look at this thing, I can actually split each of these petals down the middle. So this particular, flower or petal in nature has a lot. It has 8 that I could find. Alrighty, let's look at these polygons now. So this is a hexagon. It's a 6-sided polygon. I could definitely draw a line of symmetry going that way, and I can also draw one going that way. So it's got 2 lines. What about if I were to make a diagonal? Does that line up? You have to really think about this. Think about, say, where this point would go if I were to fold along that line. If I were to fold, it would probably fold somewhere over here. Doesn't quite line up. The same thing if I were to go this way, like these points don't actually line up. So there's only 2 that I can see for this particular polygon. Now, this is another hexagon. I have the same ones that I was able to draw in example C, but because the segments here are all the same size, whereas they're not all the same size in example C, right? These are all different sizes, or at least some of them are different sizes. I actually have more here. So I can split each side in half, and I can also make all the diagonals. So for this one, there's actually going to be 6 different lines of symmetry. So if it's regular, which this one is, you can have a different number of them. Now this looks to me like a scalene triangle. How many lines of symmetry are there? Nope, that doesn't work. What about going, nope. And actually, no matter how you try it, you will not have any lines of symmetry. There are no lines of symmetry for scalene triangle or scalene polygons. So the lengths of the sides matter when you're looking for lines of symmetry in polygons. And let's see if we can come up with a general rule about it. So how many lines of symmetry does a regular n-gon have? So we had a regular hexagon, sixgon, and it had 6. Whenever you have a regular polygon with n sides, it's going to have n lines of symmetry. Now, what happens if you have polygon with n sides and none of the sides are the same length? That's like example E here. In that case, it won't have any lines of symmetry. That would be none or 0 lines of symmetry. All right, let's look at another kind of symmetry called rotational symmetry. An object has rotational symmetry if there's a center point around which the object is turned, that is rotated a certain number of degrees, and the object looks the same. This is related to the rotational transformations that we looked at in a previous video. Here's an example. I've got this little pinwheel shape. If I were to rotate, and remember, rotations in the positive directions are going that way. If you think about where this is, and I turn this 45 degrees, does this shape and this shape look exactly the same? And they're congruent looking shapes, but if you were to lay one on top of the other, would all the points line up? And the answer is no. But what happens if I take this and I go a quarter turn, 90 degrees, and I get a shape like this? If you look at this one and this one, they are exactly the same. If I were to pick up one and put it on top of the other, all the points would have a match. That's what I mean by you get two objects looking the same. Now, if I was to turn this 180 degrees, that would be going this way, then I would get this shape. And it also looks the same. The order of symmetry, that's going to tell you how many different ways this thing can be rotated and so that it looks the same. With this particular shape, here's way 1, right? You can rotate a quarter turn. That would be way 2. You could rotate halfway around. That would be way 3. And you can go 3/4 of the way around, and that would be way 4. Now, if I go a full 360, that is the same as way 1. So I don't count what happens if you rotate it 360. This particular shape here has an order 4 rotational symmetry because there are 4 ways that I can rotate this object that it's going to look exactly the same without repeating any of those ways. We've got some other examples here. We've got a sign of some kind here. So you have to figure out, well, how many different ways can I turn this around? Here's like way 1 just as it is. I can go a quarter turn, I can go halfway, and I can go 3/4 of the way. If I go the full way around again, well, that 5th way is the same as way 1. So this has an order of 4. And now the question is, well, what are these degrees of rotation? Way 1, that's just the start. So that's 0. We don't have to worry about that one. But what's this one? That was a quarter of the way around. It's 360 all the way around. If I went a quarter of the way around, that would be 90. So my first degree of rotation is 90 degrees. I could also just keep adding 90. That's how I got the 180. And I can add 90 again, and that's where the 270 is coming from. So I have a 90-degree rotation. A little messy here. Let's just try that again. Just write it a little neater. So I have 90, 180, and 270. So again, 90 is this one. Add 90 to that, you get that one. Add 90 again, you get that one. But I don't add 90 again because that would give me 360 going all the way around, which is the same as 0. I don't have to count the present way. So these are the degrees of rotation for this particular figure. If we look at the second one, which looks like a hospital sign. Now, if I were to rotate this 90 degrees a quarter turn, would I get the exact same figure? I wouldn't, because a quarter of a turn would look something like that, right? This one doesn't have an order 4. It has an order 2 because I've got the start way, and then I can turn it 180 degrees, kind of basically turn it upside down. It's going to look the same. And the only other way is to just go back to the original start. So I'm not going to count that again. I already started it the first time. It's order 2. Now, what would be the rotational angles? Well, so the first time through, halfway is 180 degrees. And again, you can use 360 divide by the order to get that first degree of rotation. Now, if I add 180 again, I get 360. 360 is the same as my 0, so I don't count that. So there's only 1 degree of rotation to think about. This third one here, example C, it looks like a roundabout sign. How many different ways can this look the same? I can rotate this once, and I can rotate this twice. And if I do it again, I get to my original location. That's 3 different ways. And to find those degrees of rotation, you find the first one by saying, well, what is 360 divided by 3? And that would be 120. So that's that first degree of rotation going that way. Add another 120, and you get 240. That would be the second degree of rotation. And then if you add 120 again, you get to the 360, which is the same as the 0, what we started with, so we don't have to list that. This last one looks like we've got horses ahead. What is the order of this one? Well, there's really only one way that we can look at this and see the horse right way around. Any other way we rotate this, it's going to look different. There are no degrees of rotation here because it's 0 and 360, and that's it. There's only one way where this will have rotational symmetry. So basically, we say this one has no rotational symmetry because there is no way to rotate this other than its original position where it will look the same. Let's look a little bit more at rotational symmetry. A geometric figure has rotational symmetry if the figure is the image of itself, and that just means it looks the same under rotation about a point, which again, that means around a point, through any angle whose measure is strictly between 0 and 360. So we're not going to keep going around the circle several times. How many times will it look the same? So let's look at this for regular polygons. For regular polygons with n sides, the order of rotation is, well, let's look at a specific example and see if that helps us to think about it. Here's my regular hexagon. I'll just call it a sixagon here, so we're reminded it has 6 sides. Now think about how many different ways. So if this is our top, you can go 1/6 the way around, another 6, another 6th, another 6th, another 6th. You can do this a total of 6 times. This will have an order of 6. There's 6 ways that I can rotate, and it's going to look exactly the same. And what's the order of rotation? Well, let's first do this. So I can rotate it 6 different ways and get 6 different images that look the same. So if you have n sides and it's regular, same thing is going to happen. So if you have a regular polygon and you want to know its order, it's going to be n, the number of sides. Now, to find the degrees of rotation, you always get it by starting at 360 and divide by what you got here. So I know my order is 6. That means my first degree of rotation is 60. And then you just keep adding that same degree of rotation because it is very symmetric. It's going to be that same angle over and over again. Until you get to 360. So if I was to add 60 again, I would get 360, but that's that position I started with. So these would be all the degrees of rotation. The first degree of rotation would be that one. If you want to find the degree of rotation for a regular n-gon, you're going to just do 360 over n. So the answer to this question is all that stuff I wrote on the side there. Maybe I'll write it slightly more legibly over here. But the general case, again, just get your first degree by doing 360 over n. This is for regular polygons. And then just keep adding that again and again and again to just short of 360. The next topic is point symmetry. And this one we have seen when we looked a little bit at rotational symmetry, where each point has a matching point the same distance from a central point. What does that mean? If you remember rotational symmetry, this was the same as order 2, and things start looking upside down. Here is an example of that pinwheel we looked at before. Does this have point symmetry? And when you are answering that question, you want to know, does it have 180-degree symmetry? Does it look the same upside down? So here's my 0. An 180-degree would be a half turn. So I've got one here. Are these looking exactly the same? Why, yes, they are. So this one does have point symmetry. Now this is an example of a playing card. Does this have point symmetry? One way to tell is to either stand on your head or turn the card upside down. Does it look exactly the same? And this card does. And if you think about how playing cards work, you don't want to have to worry about which one's the top and which one's the bottom. You can put them in your hand any way you want. But you do have to be careful because it depends on what suit you're looking at. And some words even have point symmetry, and this is pretty neat. Is the word the same upside down? If you look at the word mom, and for now, let's just play along with the M's. When you turn them upside down, you get perfect W's. The word mom, when you turn it upside down, you get wow, which maybe that's true. Is it a word that shows rotational symmetry, point symmetry? So no, this one does not. It's a different word upside down. But if you look at the word mo, and again, the M's, just make them go down a little bit. If you turn it upside down, it actually says mo again. Yes, that one does have point symmetry or 180-degree rotational symmetry. The word swims. Again, if we make our M just point going down all the way, if you turn that upside down, it still says swims. So if something has point symmetry or 180-degree rotational symmetry, if it looks the same upside down. I have just a few U-tries here that I would like you to try. If you don't have the worksheet, go ahead and pause and see how you do. I do have some on the next page as well. So I'll put those up so that when you're working these at home and you want to pause the video, you can see all of them. But go ahead, pause your video, and then we will go through them. And we are back. Let's see if we can answer the questions about this first shape in example A here. Does this shape show rotational symmetry? What is the order of this thing? If the order is more than one, it does have rotational symmetry. We can actually rotate this 180 degrees and we're going to get the same thing. This does show rotational symmetry. And it has order 2 because there's 2 ways it can look exactly like that. The degrees of rotation, well, you could start with just saying 360 over 2. It's 180 degrees. If you add 180 to that, you're back at 360, which is the same as our starting position. It's order 2 with only 1 degree of rotation, 180 degrees. Well, what about the second shape here, this triangle shape? Does it show rotational symmetry? And this one does as well, but this one is in order 3. Because there's 3 different ways that this shape can look exactly like that. The first way would be if you use the first degree of rotation, which would just be 360 over 3, a third of the circle. That would be 120 degrees. So if you were to rotate this 120 degrees, it will look exactly like that. Add 120 again. This would be going 2/3 of the way around, 240 degrees. It will also look like that. Now, if you add 120 another time, it gets to 360, which is the same thing we're starting with. These would be the degrees of rotation for that one. This hubcap, does it show rotational symmetry? I think it does. We can actually draw those lines of symmetry. It's a lot like our starfish. So it looks like we have 5 lines of symmetry here. Its order is going to be 5. Because there's 5 ways that we can rotate and still get that same looking shape, right? Our degrees of symmetry, you take the 360 over 5. That's how you find the first one. And 360 over 5 is 72 degrees. So that's my first rotation. The next one, just add 72 to that. 144 degrees. The next one, add 72 to that. 216. Add 72 to that. Now, if I was to add 72 a third time, it would be 360 degrees, which is the same as my starting position. So these are all the degrees of rotation for order 5. All right, let's look at the last few of these. I'm by a swimming hole here, and there's a sign up. What is so special about this sign? Well, if you could turn this upside down, it says the same thing. Now no swims on mud. It says the same thing if you turn it upside down. So it's special because the words on the sign have point symmetry. Point symmetry. You could also say it has 180-degree rotational symmetry. Do the following words show point symmetry? Which is asking, does it have 180-degree rotational symmetry? Or another way to say that is it the same upside down? So the word math, if you turn it upside down, you don't get math again. So that's a no. But if you look at noon, you turn it upside down, it does. So you might remember earlier on in the video, we talked about N and S and Z. Those letters are a little bit difficult when we asked, do these have line symmetry? Because we wanted to say yes. And the reason we got confused is that words like this have point symmetry. Your brain is recognizing that there's some symmetry going on, but it's a point symmetry rather than a line symmetry. Okay, looking at these two cards, which of any of them are showing point symmetry? Now, this first one doesn't, but the second one does. And that's because the shape of this heart in the middle versus the shape of the diamond in the middle. This heart over here, when you turn it upside down, it's not going to look the same. So the shape of the suit itself doesn't have point symmetry. So this card doesn't. It almost does. But the diamond is the same upside down. It has that 180-degree rotational symmetry. So only one of them actually has the point symmetry there. And that is symmetry. I hope you found this helpful, and thank you for watching.